On scales far beyond human perception, there are strange beasts. Exquisite palaces, wondrous landscapes. Some just a few thousandths of a millimeter long. Others dominate the vast expanses of the cosmos. Thanks to groundbreaking new technologies, I'm setting out to explore these hidden worlds for the first time.
You're looking at the craters and bumps and hills on the skin of bacteria.
Mind-blowing to look at that.
Each one of these dots is a galaxy. We have an instrument here that allows you to look at an atom.
We can block the COVID-19 virus itself.
And at the tiniest and the largest scales, I'll see how physics has bizarre consequences.
My journey will take me to the frontiers of modern science, revealing our latest discoveries and our biggest unanswered questions.
This is the story of how the universe works at scales we can't normally see, from nanoparticles to galactic superclusters. These are the very first images ever recorded of the microscopic world. They appeared in a book called Micrographia, written by the 17th century scientist Robert Hooke using the first microscopes. Even at this magnification, they seem so unfamiliar.
With micrographia, 3.5 centuries ago, Hooke started us off on a voyage of discovery into the universe at ever smaller scales.
As we began to see the microscopic world, we realized that it's very different from our own. These tiny insects have evolved extraordinary adaptations to navigate the world at scales we can barely imagine. Because when you're this small, the laws of physics have unexpected consequences. This is a type of wasp called Megaphragma, one of the smallest flying insects in the world. It's just a few tenths of a millimeter long, some 5 or 10 times smaller than a flea. It has wings like paddles and flies in an unusual way.
That's because air feels very different to it than it does to us. We're barely aware of the air around us as we move through it.
And that's because of the science of air resistance. Take a golf ball and a ping pong ball. It's easier to throw a golf ball than a ping pong ball. They both have the same surface area and so feel the same air resistance. But the ping pong ball is lighter, with less momentum, and struggles to push through the air. Megaphragma is like a tiny ping pong ball, with little momentum for its surface area. So to it, the air feels more like a liquid. And it's evolved its unusually shaped wings to swim through it.
If you were to make this the size of a human, then it'd be barely able to move its wings, let alone use them to fly. Yet it's so successfully adapted to the world in which it exists that in recent years, entomologists have found them all over the world, from Africa to the Pacific to South America, even in the woods outside London.
When we look at even tinier objects, 10 times smaller than Megaphragma, we come to the scale of a typical animal cell. As we increase magnification, the laws of physics become ever more strange. Professor Susan Anderson at the University of Nottingham uses powerful optical microscopes to study human heart cells.
So what is it we're seeing there?
So this is the sort of detail that we get in a light microscope. We have lots of individual cells here, so we can see individual cells. In each you can see nuclei, so these are the nuclei. The little bright spots are the nucleoli. This is the edge of the cell, and then the cytoplasm of the cell, you can't really see any detail inside.
So why is it that you're looking at these?
The useful thing about this is that we can see cells, dynamic cells. So the cells that we're looking at here are human heart muscle cells. So we can actually see them beating.
Oh, wow. Right, yes.
Yeah.
Seeing them beat in such detail means scientists can begin to understand why they go wrong.
You can see the nucleus, you can see the outline of the cell here. You can see lots of them beating at about 30 beats per minute, which is about half the rate of a human heart.
They're from a living heart?
It would be difficult to do that ethically. So what we do is we obtain stem cells from human skin. We reprogram the human skin cells back to stem cells, and then we direct them down a differentiation pathway to being muscle cells. And we can obviously see that they are contracting and beating like a heart muscle cell.
What's actually happening here?
The cytoplasm contains lots of contractile filaments, and they're shortening and lengthening so that the cell beats. There's a whole community of cells here that are talking to each other, and they're passing that signal from cell to cell, and they're beating en masse.
How does it make you feel when you're looking at these living cells?
I love them. They've got personality. You know, they do what they want. If the light here is too bright, they will just move. They will just walk away. They're very entertaining.
Microscopes are key to understanding cells because right across the living world, they're tiny compared to most everyday objects. For instance, a 200-ton blue whale and a tiny megaphragma are both made of cells that are similar in size, roughly between 100th and 1/10 of a millimeter across. Why are cells this size?
The answer lies in the fact that in certain crucial ways, small things are much more effective at interacting with the outside world than big things. Here is a lump of titanium. It's a very reactive metal, and I'm going to try and burn it. Nothing. But here is also titanium, but it's been crushed down into a powder.
Powdered titanium has far more of its surface relative to its volume exposed to the air. So it's got much more access to the oxygen in the air to help it burn. This applies to cells too. Cells absorb nutrients and oxygen from the outside.
Being small and therefore having a large surface area to volume ratio means they can do this very effectively. If they were significantly larger, they wouldn't be able to take in what they need to survive.
Ultimately though, there's a limit to how small they can be. Cells are full of stuff, the nucleus, mitochondria, ribosomes, so it's a balance between making them small enough to maximize their surface area to volume ratio, yet big enough for their parts to perform their function. And their shape is crucial too. For instance, some cells have found a way to increase surface area without changing volume. The cells in the walls of our digestive tract absorb the nutrients needed to sustain our entire body through their surface. So this surface needs to be as large as possible.
How do they do this? How can cells maximize their surface to volume ratio without getting any smaller? Well, imagine this balloon as one of those cells. How can I increase its surface area without making it significantly smaller? Well, I can give it fingers. I've calculated these 5 fingers increase the surface area of this rubber glove by about 50%. And remarkably, Evolution has adopted precisely this strategy. Welcome to my digestive tract. These protuberances are called microvilli. They're each about 1,000th of a millimeter long, but just a few molecules wide. And there are millions of them. They stick out from the cells, dramatically increasing their surface area and therefore their ability to absorb nutrients.
Of course, the real thing is rather more impressive. Scientists have calculated that because of the microvilli, our intestines have increased their surface area by up to 15 times. Modern optical microscopes have uncovered a strange world, just a few thousandths of a millimeter in scale, a world very different from our own. All revealed by a device that is essentially remarkably simple.
This is a modern but pretty basic compound microscope, and it works on the same principles as Robert Hooke's microscope from 400 years ago. It's so simple really because you just have two lenses, one in front of the other, and adjust them until you get the sharp magnified image.
The second lens multiplies the magnification of the first. There is, however, a fundamental problem with optical microscopes. As we increase magnification, images get more and more blurry. This is because light is a wave, so objects which are smaller than its wavelength are impossible to see clearly, which means optical microscopes hit a wall at about 1,000th of a millimeter. So the next step downwards means ditching light entirely and finding something else to see with, like tiny subatomic particles, electrons. I found a bit of old technology, something older viewers might recognize.
I've taken the back off this old TV set. So what you can see here is called a cathode ray tube.
This bit, the cathode, boils off electrons, which are then accelerated in a vacuum
to hit the phosphorus screen at the front. Now, ordinarily on a TV set, the electron beam scans across the whole surface of the screen to produce the picture. But I've rigged this now so that it produces just a single narrow beam of electrons forming a spot in the middle. Now, because electrons are negatively charged, they're affected by a magnetic field. In fact, that's how we control the direction of the beam. And to show that, I've got a small magnet at the end of this stick, which I can use to distort and move the direction of the beam. In fact, you can see it's produced 3 spots. That's because there are 3 electron beams, because this is a color TV. Now I've got it working normally. The electron beam is scanning across the whole screen to produce the full picture. But I can still distort this picture using my magnet. So if magnets can be used to control and direct the path of an electron beam, they can also be used to focus a beam of electrons in the same way that a glass lens can be used to focus a beam of light. And this means that we can use electrons to make an electron microscope. This is a modern electron microscope. And in many ways, it resembles Robert Hooke's optical microscope from 400 years ago. But this one uses a beam of electrons, just like in the back of that old TV set.
Here's where the electron beam is generated. Electromagnetic lenses focus the beam here. This is where the object is placed. More lenses here magnify the image thousands of times, and this is a screen which turns the electron image into something we can see.
With microscopes like this, scientists were suddenly able to see objects hundreds, even thousands of times smaller than they'd ever been able to before.
We could see tiny details on the bodies of insects and the machinery within cells that made them function. And then we came face to face with one of our deadliest enemies. This is an infectious bronchitis virus, and these are common cold viruses. On them, you can see something strange, a kind of halo surrounding the virus.
There were, in fact, tiny spikes, each one just 100 millionth of a meter across. And they gave the virus a crown shape. So they named this new class of viruses after the corona of the sun. These are all coronaviruses.
In 2020, electron microscopes helped to identify a new virus.
SARS-CoV-2, or COVID-19.
Professor Pippa Hawes studies viruses like COVID-19 for the Pirbright Institute.
How have electron microscopes allowed us to understand COVID-19?
They've been crucial because they've allowed us to investigate the structure of the virus so we can actually identify it. So here we have the COVID-19 virus itself. We can see the spike protein very, very clearly here around the outside of the virus. And inside is the viral RNA.
Like all viruses, COVID needs to hijack another cell to reproduce.
What does the virus do inside the cell?
It takes over the cell machinery. The RNA gets placed inside the cytoplasm of the cell. This RNA is read by the cellular machinery, and it's translated into viral proteins that the virus is using in order to replicate.
So by giving it its RNA, the virus is basically reprogramming the cell to get it to do its bidding.
Yes, exactly.
Incredibly, we can now see exactly how this happens.
So what are we looking at here? Where's the cell and where's the virus?
The outside of the cell is sort of outside of our field of
okay,
view.
right.
Yeah, so this is zooming in now on an infected cell. These are parts of the cell that the virus has taken over and formed into these double membrane vesicles.
So these vesicles then are like the virus's nest that it builds to make a home for itself so that it can replicate.
Yes, exactly. It's sometimes called a factory. It's where it produces more copies of the viral proteins, it produces more of the RNA, and where it all comes together in the new viruses.
And can we see the individual viruses?
Yes, if we go... Ooh. Here, these two are viruses that are actually budding into this vesicle. So these are forming viruses.
Sneaky.
Yes.
And so understanding this, I mean, does it allow us then to combat COVID-19?
We need to know how the virus infects, how it replicates and how it leaves, which would help with antiviral treatments to prevent the disease.
Seeing things at this scale has revealed an incredible new world to scientists. They could see and begin to understand how genetics worked by seeing single chromosomes. They could watch a white blood cell attacking an infection. And they could now see beyond the living world, deep into the materials that surround us. How cracks move through metals. Then, in 1991, a group in Japan saw this. Strange shapes forming at the end of a sparking filament. 10 times smaller than a virus, they were carbon nanotubes, each a long cylinder whose walls were just a single carbon atom thick. And they had unexpected properties, which has led to an explosion of fascinating new materials.
This is one of the blackest materials in the world. See, it might look to you like a flat black square, but in fact, if you look at it side on, or even at the back, you can see it's got contours, it's got dents. And yet, looking at it face on, there's nothing, just pure blackness. Now, normally when we see objects, light bounces off of them into our eyes at different wavelengths and different angles, so we can see color and shape. But this is like a Harry Potter spell. Light falls on the surface and then just disappears forever.
What's perhaps most surprising is that this paint is made of nanotubes. The paint, called Vantablack, is the invention of nanotechnology scientist Ben Jensen.
So it just looks like a black surface here, but talk me through what it looks like if you zoom in.
So if you imagine a forest of trees, but the trees are thousands of meters tall, and they're all straight and they're all equally spaced. So light comes in, photons come in, and they effectively bounce between the trees, and then they're absorbed after a number of bounces. So as you can see on here, it looks like a very, very thick, lush carpet. So light coming in gets in between the nanotubes and bounces around and is eventually absorbed into the substrate.
It looks like a brush.
Yes, exactly.
I want to get across to you just how black this material is. This card has been painted with the blackest commercially available paint. It's called Black 3.0. And yeah, it looks very black. But put it alongside the Vantablack, and if I shine a light on them, you can see the paint just looks grey in comparison. And even more impressive, if I make an angle so that the light bounces off the surface and hopefully into the camera, you can see that this paint looks a lot brighter because the light has been reflected. But if I do the same thing with the Vantablack, you should see no difference at all. All the light is being absorbed, none of it is reflected. What is it useful for?
So its main uses are in satellite systems for controlling stray light from the sun, the moon and the earth when you're looking out at stars. It's also used for calibrating infrared cameras that look at the earth for global warming studies. And terrestrially, it's used to protect cars with autonomous driving modes from sunlight entering the camera systems and causing ghosting and loss of signal.
For me, this is an entirely unexpected and surprising property of nanotubes. And more importantly, this is nanotechnology that we can see, or rather not see.
Glimpsing tiny nanotubes was impressive, but could we go even further? By the 1980s, scientists were trying to see ever smaller things using a completely different approach.
They wondered if they could see by feeling. Basically, the idea was to mimic the way the needle on an old record player works.
A stylus passes along a groove on a record, and the tiny bumps vibrate the needle, making music.
But of course, the tip of a record player stylus is far too big to feel something as small as an atom.
But then in 1982, two scientists, Heinrich Rohrer and Gerd Binnig, had an ingenious idea. They put a thin metal spike into a corrosive liquid.
Using electrical currents, they slowly dissolved away the tip of the spike so that just a very thin needle of metal remained. Its tip was just a few atoms in diameter.
But how could this needle see? One idea was to harness an unusual force of nature.
This is a gecko. Its feet stick to the glass using a tiny attractive force called the van der Waals force.
Van der Waals forces exist because of a rather quirky aspect of atoms and molecules. Think of an atom as a tiny positively charged nucleus surrounded by a cloud of negatively charged electrons.
But crucially, these electron clouds aren't static. They fluctuate in shape, often randomly. So the clouds can become lopsided with more electrons on one side than on the other.
Because opposite charges attract, the negative end of one molecule is pulled towards the positive end of another.
The force that an individual atom feels is, of course, minuscule.
But these effects can add up.
And this, in turn, means that the molecules on the surface of an object can sometimes feel pulled towards the molecules on the surface of a nearby object.
And that's what the gecko is taking advantage of.
A gecko's feet are covered with billions of tiny structures called spatula.
When these press against the glass, they flatten out, creating a huge surface area. Billions of atoms are now in contact. Then the tiny van der Waals forces combine and hold the gecko in place. And this was one of the forces Binnig and Rohrer believed they could harness.
When a tiny stylus, and remember its tip is just a few atoms wide, approaches atoms on the surface of the material, this is when the van der Waals forces come into play. Just like the spatula on the foot of a gecko feels an attractive force between it and the molecules on the surface of the glass, so the stylus feels a force pulling it towards or pushing it away from the atoms as it passes over the surface.
Measuring minuscule forces like these can paint a picture of the surface at the tiniest scale. This is a modern atomic force microscope. Dr. Georgina Ben is using it to understand one of our deadliest enemies.
I'm going to be imaging E. coli, which are a type of bacteria. So with a normal microscope, we could look at just the bacteria, but we need our atomic force microscope to be able to see the details on the surface.
Why are we looking at the surface of E. coli?
So E. coli are really good at resisting antibiotics because they have this extra protective layer around the outside. And we want to know how the protective layer is arranged so that we can help people design antibiotics that can get through the protective layer more efficiently.
So this is the full cell, the full bacteria.
Yeah. So you can sort of start to see features on the surface. And these are already well below optical microscopy kind of sizes. Right. My scan's going to be 500 nanometers wide.
So we're now looking at the surface of the bacteria.
Yes.
This is really impressive. What we're looking at here is bacteria skin, and it's, you're looking at the craters and bumps and hills on the skin of bacteria to find these weak spots that we can attack with antibiotics.
Each one of these black spots is a hole on the bacteria, which is about 3/millionths of a millimeter wide.
These are the holes that let water and nutrients in and out of the cell. So we're looking at how they're arranged relative to each other. And what's interesting is that you've got this really tight lattice of pores, and then sometimes there are these gaps in your lattice.
So those are the weak spots?
We don't know. So we want to know, that's like a next question, is why these are important, why they would be there in the first place. So we know that some kind of patches will make the membrane weaker, and some of them will not.
So if you could get the bacteria to mutate so that it generates these weak spots,
or
then
maybe,
you can attack it.
Yes, or maybe get a drug that will make these weak spots, and then we could apply antibiotics.
With the atomic force microscope, we began to see more detail of the world than ever before. But it had its limitations. They are most effective at seeing features on a flat surface.
But atoms also connect up in 3 dimensions, often forming very complicated shapes, which in turn affects their behavior. How then can we see these shapes? Remember how visible light has a limit because of its wavelength? Well, it turns out there's another form of light which has a much, much smaller wavelength.
X-rays.
Crucially, X-rays have very short wavelengths when compared to visible light. Now, the wavelengths of visible lights are just under a millionth of a meter, but the wavelengths of X-rays are typically several thousand times shorter, at around a tenth of a billionth of a meter. But there are many differences. Our eyes can't detect X-rays. More importantly, they pack a punch. X-rays contain much more energy than rays of visible light. The intense energy of X-rays enables them to pass unhindered through soft tissue like flesh and blood, which is as transparent to X-rays as glass is to visible light.
The larger atoms that make up our bones do stop X-rays. So when you see an image like this, you're literally seeing an X-ray shadow cast by your bones on photographic paper.
This begs the question, can X-rays, which have such short wavelengths, be used to see things that are just too small for visible light?
The first hints that this might be possible came in the early 20th century. Scientists noticed that when they shone X-rays through crystals, they produced weird spots arranged in patterns.
These images may not look like much, but think of them as a kind of code. And by cracking it, you can deduce the way the atoms in the crystal are arranged. This process of turning images like these into an understanding of how substances are structured down at the atomic scale is known as X-ray crystallography. For a sense of how X-ray crystallography works, let's say each of these Christmas trees represents one of the atoms that makes up the crystal. To keep it simple, let's say they're all arranged in neat rows, just like these trees. What's important is that the wavelength of the X-rays striking the crystal is about the same as the distance between the rows of atoms, or the rows of trees in our analogy.
Imagine an X-ray reflecting off the surface and the layer beneath. The beam that travels down to the next layer has a longer journey, and that is key. If the waves are now out of step and the peak of one coincides with the trough of the other, they then combine and cancel out. But if they're in step, the peaks combine, making a larger wave and a bright dot on the screen.
By carefully measuring the angle at which the X-rays strike the crystal, where the dots appear, where they disappear, you can deduce the structure of the crystal. By decoding images like this, scientists in the early 20th century were able to deduce the structures of simple crystals like rock salt. The atoms are arranged at each corner of a cube, and the cubes repeat to form a 3D lattice. Most importantly, it meant we now knew the distance between the atoms. It's a third of a billionth of a meter.
But for me, the story of X-ray crystallography really comes into its own because of one of the great heroes of British science, Dorothy Crowfoot Hodgkin. At Cambridge and Oxford in the 1930s and 40s, Hodgkin became fascinated by X-ray crystallography, and she quickly established herself as one of the leading researchers. Her first big challenge came during the Second World War and her work on penicillin.
Scientists had already noticed that the newly discovered penicillin had incredible antibacterial properties. It could stop infections in their tracks, literally bringing patients back from the brink of death. Now, in the throes of war, understanding it and producing it in quantity was more important than ever.
But penicillin was still a mystery, with a handful of atoms arranged in an unknown structure. So Hodgkin set her laboratory a challenge: use X-ray crystallography to learn its structure. Georgina Ferry is a science writer and biographer of Dorothy Hodgkin.
Tell me about penicillin. What was so difficult about understanding its structure?
The structure was unknown. And naturally, the organic chemists all came to Dorothy and said, would you like to have a go at this? The first problem with it was that it doesn't make terribly good crystals. These are not ideal for putting into the X-ray apparatus. It took a while before they managed to get a version of penicillin that she was able to get a good image from. That image looks like this. These are spots on photographic film that have been made by X-rays coming out of the crystal and hitting the photographic film. The dots are at different intensities. Some of them are very black. There's some down here that are very faint. And what she had to do was carry out a complicated mathematical calculation, which then enabled her to begin to understand where there was what's known as density in the molecule and in the crystal. And density means there's an atom there. And the final stage, once you've done all those calculations, is to essentially draw a contour map. This represents a slice through the molecule, and the numbers that are written down represent the density of the electrons. And what she's done is join up areas of equivalent density, and that shows you that's a place where there's an atom because there's a lot of intensity there.
We're looking at a 2D picture here. So how did Hodgkin then go to the full 3D structure?
What you want to do is take a number of slices, stack those one above the other, and that'll show you the three-dimensional structure of the molecule. So you can see what we've got here is a stack of perspex sheets at equal distances apart, and on each sheet you've got the contour lines drawn, as we were looking at before. And if you're looking down from the top, you can see the three-dimensional structure.
This is the structure of penicillin that Hodgkin came up with after some 4 years of research.
These are the carbon atoms, and they're connected by chemical bonds to other atoms.
Oxygen, hydrogen, nitrogen, sulfur.
But it's this section here that explains its incredible efficacy. It's called a beta-lactam ring, and it seems to give penicillin its wondrous ability.
It binds to a part of the cell wall of most bacteria, killing them dead. Understanding how penicillin works was a revolution in medicine. Hodgkin's work spawned a generation of new antibiotics, effective against many aggressive bacteria, saving millions of lives. And these techniques, still widely used today, famously went on to unlock the structure of DNA. Despite the achievements of X-ray crystallography, it was still an indirect method of seeing and only worked for crystals. To see even smaller things would require something else. It seemed electron microscopes held the most potential. But they had a huge technical problem. Their electromagnetic lenses were fundamentally different from glass ones.
One of the most common problems that affects lenses is called spherical aberration. You see, the way lenses work is that they bend the light that travels through them, but the amount of bending depends on which part of the lens the light travels through.
So when I try to focus the sun, for instance, I can never quite focus to a point, which means at high magnifications especially, parts of the image will always blur.
Electron microscope lenses are exactly the same. They also suffer from spherical aberration.
And at high magnification, the blurring was making the images unusable.
Now, for glass lenses, this issue can be minimized. You add a second lens, a concave lens, which corrects for the first one, giving us a much sharper point.
But this solution doesn't work with electron microscopes.
The lenses of electron microscopes are fundamentally different from glass ones. There simply is no equivalent of a concave lens. The physics of electrons and electromagnetic fields forbids it. So it seemed that electron microscopes would always suffer from blurriness at very high levels of magnification. The question was whether we could delve deeper to see even smaller. Well, the next breakthrough that changed everything took place here in Germany.
Two teams of headstrong scientists started to question the orthodoxy. There were three in Germany: theoretician Harald Rose, experimentalist Max Heider, material scientist Knut Urban, and an American team led by Andrei Krivenik.
Everybody expected us to fail, and so we knew we could only exceed expectations.
Each stubbornly believed that they could somehow overturn the established prevailing science and make an electron microscope that could see more, perhaps even atoms.
Was it a big challenge then to persuade the science world that here was something that was going to change the field?
The science world at that time had essentially given up to have aberration-corrected electron optics.
They decided that hardware aberration correction will be unthinkable.
They said it was impossible.
It was possible. We had three different people: theoretician, experimentalist, and material scientist. And I think these three together, that was just the point for the success.
Their approach used multiple electromagnets, multipoles, to distort the image, squeezing out the worst of the aberration. Then a second lens reformed the image, now almost aberration-free. But getting it right was challenging. It would require sophisticated arrangements of multipoles, sensitive cameras, and powerful computers.
And here, for example, we have one hexapole, and as you can see here, we have 6 poles with 6 coils. They are just connected to each other, and then we have a north, south, and the beam passes through this hole here. That means first we change the shape of the round beam to a triangular shaped beam, and then to combine it with second hexapole to have a round beam again.
For years, they struggled to get their new lenses to work, and the rest of the scientific community remained skeptical.
I had a lovely comment from a professor at Stanford who told me, Andre, you're bearing your career.
But then, in June 1997, their stubbornness began to pay off. And soon they caught glimpses of the building blocks of all matter with unprecedented clarity. Here's a typical image without aberration correction. Now watch as it's added in. The white blurs resolve into 2 clear dots, each one a single atom of silicon.
Finally, you could see atoms.
This was a real jump in innovation. This was a real paradigm change.
What was it like when you saw those first images?
Seeing is believing, and the mission impossible was not impossible.
They had achieved a scientific miracle.
It was like if you have a huge fog, but suddenly the fog goes, suddenly you see everything.
A new kind of electron microscope.
It was brilliant, everything was so unbelievable. And this is the most important effect of aberration correction.
By 2020, they'd gone from academic outcasts to world-renowned scientists.
The images that came out are truly spectacular. Like one of them on the cover of Nature, that's kind of like if you're a model and you get on the cover of Vogue.
And they had defined a new kind of science.
I think we are on the way to make high-precision electron microscopy a part of science in general.
The next stage of this journey downwards happened in Manchester with the discovery of an incredible new material, graphene. The new electron microscopes revealed that graphene was a sheet of carbon just a single atom thick. And incredible strength was just one of its unexpected properties.
So, just how impressive is graphene? Well, I've come here to this lab to carry out what's called a stress test. I've got 2 strips of plastic here. It's a stretchy polymer. One of them is just the pure polymer. The other contains just 3% graphene mixed in with it. And I want to stretch them to find out how much force is needed to snap these strips.
First up is the pure polymer.
There we go.
It's gone.
It's gone.
So that snapped at
533 newtons.
533 newtons. So that's about two
bags of cement.
2 bags of cement. So now you're going to swap it with the graphene.
Yes, I'm going to reset the machine with the graphene ones. Okay.
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 Okay, so it's now hit 500 newtons. We've now already overtaken the non-graphene.
Yes.
And it looks pretty healthy as far as I can tell.
It's healthy, yes.
It's coming up to 750 newtons now.
We're now...
And now it's come up to 1,000 newtons and still going strong.
And
oh, so that was about...
So the final force was 1,074.
So that's double. Twice as much force was needed to snap this polymer compared with the one without the graphene. That is pretty impressive. A huge improvement with just a few percent of graphene mixed in with the polymer. That's incredible.
Graphene has shaken the scientific community to its core, and yet was discovered almost by chance by scientist Andre Geim as he was searching for ever thinner slivers of graphite.
Talk me through what happened on that night when you realized your eureka moment.
20 years ago, I realized that just taking Scotch tape, putting piece of graphite between the Scotch tape, peeling the Scotch tape like that, leaves small pieces of graphite.
Is it something we can demonstrate here? Because we have a piece of graphite.
Yeah. You can take this piece of graphite and without much trouble, you can, of course, make it thinner by repeating this procedure. But if you shine lines through, you eventually start finding flakes which are transparent. And that actually was eureka moment, because being reasonably well educated, I realized that if flakes of graphite transparent, they are really, really thin. Probably initially those were 10 layers thick, but eventually we went down to a single layer.
It's hard to overstate just how excited scientists and engineers are about graphene. So let me just remind you what graphene is. It's just a single flat sheet of carbon atoms all bonded together. But that would be really underselling it, because at around 1/3 of a nanometer, it's just a single carbon atom thick, making it the thinnest material ever made.
For a sense of why graphene is so extraordinary, we have to understand its physics at the atomic scale. Each sheet is made up of repeating hexagons. At each corner is a carbon atom that's bonded powerfully to 3 others. Those bonds are the source of the material's strength, but they also seem to produce other strange properties.
Each carbon atom bonds to its 3 neighbors by sharing electrons with them. But not all the electrons are used for this. 1 electron from each atom is spare. These free electrons can zip around unhindered. And this has huge consequences because it means that graphene can be made to conduct electricity incredibly efficiently.
There are high hopes that it will enable new kinds of electronic components, revolutionizing batteries with much greater storage, and also solar power generation, water filtration, material science, and quantum computing.
Of course, this is still early days in graphene research, but there is without doubt much to play for.
The discovery of graphene brings us towards the end of this story, because with the newest aberration-corrected electron microscopes, we're now able to see on the smallest scales imaginable. Professor Quentin Ramas runs some of the biggest electron microscopes in the world. He is going to zoom into a sample of graphene until we can see individual atoms.
Okay, what are you going to show me here?
So we've prepared some graphene samples for you.
The samples are on a copper grid, just millimeters wide.
Let me put it here and actually place it into the sample holder.
That's the 3mm sample.
That's the 3mm sample. And now hopefully you can already
see the grid.
So they're essentially just copper bars.
Under the optical microscope, I can just make out holes in the sheet of carbon within the grid where the graphene flakes are. To see them in more detail, he now switches the sample into a powerful electron microscope.
So what we're looking at now is the same image as we had under the optical microscope.
You can already recognize those 2 shadows here at the corners of those grid squares. But in the middle here, you recognize what you also saw on the optical microscope, which are those circle holes, inside which is the graphene that we're going to go and look at. Slowly getting closer and closer and closer. We're going to be zooming into graphene much further in.
Almost gives you vertigo when you realize how much we're zooming in. Okay, so what are we looking at here?
This is a patch of graphene that's about 500 nanometers across.
How does this then compare to the thickness of a human hair? It would be
several meters across.
Several meters across in diameter.
Yes.
That's how
small it is.
And yet we're still only halfway in our journey down. Not even halfway.
100th of the way there.
Okay.
And so what we're trying to do really is zoom in even further on that little black speck.
Go for it.
So we'll start reducing the magnification slowly. I'll go to magnify it 10 times this time, trying to not go too fast so that you can really keep.
You don't want to spoil the surprise for me, do you?
You don't want to spoil the surprise, no. If you notice the shape of this hole, it's about the shape of Africa, I would say. It's now getting to a size that is more foreign to everyday life, especially when you start realizing that this patch is going to be 100 times smaller still. So let's zoom in and hopefully see what we're here to see, which are single atoms. So this is now that same patch, and you notice that it is very dark. You might just about start being able to recognize some pattern in the middle, some very faint lines which correspond to the hexagonal lattice in graphene. But if you look closely on the original image that we still have on screen here, you see small round blobs that are perhaps a little bit brighter, and they are brighter because those atoms are heavier. And we happen to know they're silicon, but just to demonstrate, I can move that scan box around one of those single atoms, and hopefully it'll light up like a Christmas light in the middle. And there it is. Because it is heavier, it appears brighter on the image.
So that entire bright patch is a single atom of silicon. And yet it's a blob, it's a patch. It's not the picture of an atom that we learn about at school with a nucleus and electrons buzzing around the outside. So what is exactly?
It remains reasonably abstract. What we see is this average structure of subatomic particles, and that gives us this average round shape. We've magnified this sample that we've taken out from a sample box and put into the microscope by several million times to see on the screen this magnification.
So, 1/10 of a billionth of a meter. We've come a long way since Robert Hooke.
For me, as a theoretical physicist, an atom is just abstract mathematics, an equation, an idea. But to see one of them with my own eyes, the building blocks of everything, just 10 millionths of a millimeter across, is nothing less than miraculous.
I still can't get my head around the fact that I'm looking at individual atoms. Well, look, I'll tell you. I mean, I've spent my career studying atomic nuclei, but for me, it's been abstract. The notion that we're looking at an individual atom here, and I love the analogy that there are more atoms in a single glass of water than there are glasses of water in all the oceans of the world, right? Atoms are tiny.
They are tiny.
The fact that we have an instrument here that allows you to look at an atom, the novelty doesn't wear off.
It definitely doesn't. No, it might be either simple-minded or single-minded, but it's seeing those single atoms is, I think, something I'll want to do for the rest of my life, and it's just a wonderful thing to see.
We've now entered a realm in which we can see individual atoms, and it's leading us into a new world of single atom physics, chemistry, biology, engineering, and medicine. It's all so new that it's impossible to say where it's going to take us.
But as we learn more about our world, from insects to cells to the atoms that make us, I know there will be many more wonders to discover. Next time, I go big as I journey from our solar system out to galactic superclusters. I'll confront the biggest mysteries in our universe.